So here we're at our inequalities, and it says solve for the inequality when r of x is greater than or equal to 0 using the graph of r of x. So this right here is our r of x. Okay, and it says it wants to know, yes, this right here, the function, right? The graph, the function, all that's r of x, right? R of x is just the name. You don't always have to have f of x or g of x. You can name a function, whatever, just like you can name you all, whatever you want. Okay, so we're going to, it's asking us, when is this greater than or equal to 0? Which in terms means when is it above the x-axis? That's what it's asking. When is the function above the x-axis? Okay, because that's when you have values that are greater than or equal to 0, right? So when am I above the x-axis is all that it's asking. Does capiche? Yeah. Okay, so the first thing you need to do is identify your x-intercepts. So step 1 is find x-intercepts. Because your x-intercepts are what splits your function from positive and negative y values. Make sense? Okay. So they are where? X plus 3 and x minus 3. And why is that? Those are not our intercepts. Those are our asymptotes. This is it. Okay. So your denominator tells you your vertical asymptotes. What tells me my x-intercepts? My numerator. Setting your numerator equal to 0 is how you're going to find your x-intercepts. Does that make sense? So setting our numerator is how we find our x-intercepts. Next, we're going to identify our asymptotes. But first, we want to find our intercepts. So our numerator equal to 0. That means I'm going to take x minus 2 and set it equal to 0. And what do I get? X equals 2. Does that make sense when I look at the graph? Yes. Step 2 is to find asymptotes. Vertical asymptotes. Okay, so finding my vertical asymptotes, that's where I set my denominator. Well, asymptotes and wholes. Denominator equal to 0. So when I set my denominator equal to 0, that's the x squared minus 9 equals 0. So x equals 3 and x equals negative 3. Yes? Okay. Third is to make our number line. So we're going to create a number line to analyze. So on this number line, that's where you put your intercepts, your asymptotes, or your wholes, whichever one you may have. So we go from negative 3 to 2 to positive 3. So when I look at this graph, I'm determining, is it negative or positive results? Okay, so I have a graph to read. If I didn't have a graph to read, I would plug in values. Does that make sense? I have a graph to read. So coming from negative infinity up into negative 3, do I have positive or negative results? Negative. So these are below the x-axis. Make sense? And that's because the answers are negative. From negative 3 up until 2, what do I have? I have positive, so they are above the x-axis. From 2 to 3, what do I have? Negative, which makes me below the x-axis. And then from 3 to infinity, what do I have? Positives, which make me above. You have to plug in values. So if I didn't have a graph, I would plug in negative 4. Exactly. It goes back to using that same mentality. Numbers in between the two. So I would plug in negative 4. I would plug in 0. I would plug in 2.5 to determine whether it's a positive or negative. Yes. Plug it in for x. Anything? I would plug it into -4 minus 2, -4 squared. No, the number line is where we're writing our results. What is that to plug in? Yes. Shh. Hold on, guys. We do. It's 0. Yeah. So even though it's not going to always be marked, notice that none of these were marked. I wrote that one in and I wrote that one in. When you look at a graph, your asymptotes are actually not marked. They're invisible. So your middle horizontal are not as concrete as vertical asymptotes. Horizontals can cross, and it typically happens at an x-intercept that takes place in the middle because you have to have that transition in signs. Okay. All right. So the answer is, so based on our number line that we've created, if we're looking for when this function is greater than or equal to 0 in terms, that means above the x-axis. From where to where am I above the x-axis? So from -3 to 2, and it's an asymptote, so it's a parenthesis. And then where else? And then 3 to infinity. And that is my answer.
So we did plug it to number line.
You don't plug anything we read from the number line. We did not plug diddly squat. If that works in your brain, we'll let it stay there.
So we just, wait, the reason we did that is because it's all in below?
Yes.
Are we gonna do one to the one below?
No, it didn't ask us. It asked us for when is it greater than or equal to. Okay. So with that same logic, if it said when R of X is less than or equal to, then what would we have been looking for? Below the x-axis, because that's negative numbers, right? If I'm less than 0, then I am negative. And if I'm a negative y, I'm below the x-axis.
Why does the 2 bracket right now?
Because at 2, I am defined, and it says equal to 0. At 3, am I defined? And at -3, no, I'm a discontinuity. I'm a boundary line. Okay. All right. Our next example is going to be without a graph. Okay. So we're going to do one without a graph. Here we go. So we have x minus 1 times x minus 2 times x minus 4 is less than or equal to 0. So what type of values are we looking for? We need them to be negative, which means it's going to be, if we had a graph, then we would be looking for below. But do we have a graph? No. So all we're focusing on is negative outputs. Okay. So we're focused on negative outputs. And output means y, correct? Negative y values. So step 1 is to first identify your x-intercepts. So my x-intercepts are at x equal 1, 2, and 4. Step 2 is to identify any vertical asymptotes or holes. Will this graph have any? No, in A, because I don't even have a denominator, right? So there's nothing for me to do. Step 3 is to create my number line based on what I have. So we have 1, we have 2, and we have 4. So we have to choose values to the left and to the right. So a value to the right that we can use is what?
0.
Or choose 0, right? So if we choose 0 and we substitute 0 in, that gives us -1 times -2, which is what? +2. 2 times -4 gives us. So this is going to be a negative output, correct? Yes. All right. Now we're going to choose a number between 1 and 2, which would be 1.5. I plug in 1.5. That gives me 0.5 here. Yes. It gives me a -0.5 here. Yes. Are you with me? So now we're at -0.25. And then this gives me another. It gives me a negative. And a negative times a negative is a positive. So my output's going to be above.
Doesn't even matter the number.
As long as you're paying attention to your signs.
Oh, you're right.
All right. So here we go.
Oh, man.
All right, here we go. So now we're on to 3. All right, 3 minus 1 is 2, positive, right? 3 minus 2 is 1, still positive, right? 3 minus 4 is negative. So a positive, a negative makes a negative.
Like I just think
Okay, let's do 5. Let's try it. 5 minus 1, positive 4. 5 minus 2, positive 3. 5 minus 4, positive 1. Positive makes it what? Positive. Because all we're focusing on is it negative or positive? You're focusing on whether it's negative or positive. Got it? All right, so now negative outputs. Where were my negative outputs at?
infinity to 1.
Negative infinity to 1. Where else? And 2 to 4. Where? Exactly, because it's an x-intercept. No asymptotes. All x-intercepts are defined points, so they require a bracket. Because that's where we equal 0. Yes.
Why is 1.5 positive?
Why is 1.5 positive?
1.5.
So this was a negative, this was a negative, and this was, well, this was a positive, right? This was a negative, and this was a negative. A negative times a negative makes a positive. So now we're down to positives. Okay. All right. How do we feel?
Tired.
Doable?
Yeah.
All right. Next one is an example of when it's not set to 0.
I hate those.
Okay. Guess what you have to do?
Cry.
Set it to 0. Okay. When it's not set to 0, we have to set it to 0. Okay. Huh? Not just 2, because it's fractions. In order to subtract, fractions must have what? A common denominator, correct? Okay, so in order to just subtract, what is the denominator of this side? Could have been x minus 3. So if I want this to have a common denominator, I can multiply the numerator and the denominator by x minus 3. So I'm going to multiply the numerator and the denominator by x minus 3. That's because this is just 1 in a disguise, right? It's not going to change the value. All I did was multiply by a fancy 1 so that they would have a common denominator.
Wait, so saying the name of this, not like set it to 0, but like we always.
Before we can do steps 1 and 2, we have to set this equal to or 0. Okay. So now I can subtract. So when I subtract, I have x plus 1 over x minus 3 minus 2x minus 6 over x minus 3 is less than or equal to 0.
Oh, because we factored in the 2.
Ask your questions.
Wait, why is it minus? Because we're moving it to the top.
Because we moved it to the other side.
Oh, okay. We put it all under one equation.
Yes, but I didn't want to write it as one big one and freak people out.
Oh, that's funny.
And would it be x plus 1 minus, or would we combine the like terms on the top?
Yes.
So we're
Okay.
just.
Yes.
Why is there a minus sign? Because it was on the right.
Because I moved it from the right to the left. And when I move something, I subtracted it, right? I do the opposite of what it was.
Wait, so, instead of doing like it's 2x squared minus, where we just gonna do minus.
What do you mean?
Cause if you, like, when you technically add together and make, oh, it would be 2x, not that's clear. No. Technically, you'll say it was the x in the bottom.
It's all together. Okay. All right. I'm getting a lot of weird questions. So here we go. The other thing is when I subtract the 2, this is what's happening. This is the shortcut. So if you ever remember me talking about chopsticks in a bowl, this is for the people who struggle with realizing what's happening. That's minus 2 over 1. So chopstick, I cross multiply. That gave me x plus 1. Yes? We see that? And then we minus Then I cross multiply, that gave me 2x minus 6. And now my bowl is the same. Are my denominators now the same? Yes. So now when I do the math, this is x plus 1 minus 2x plus 6. Remember, this negative applies to both, not just one. You have to distribute the negative. Okay? Guys, hey, I get when you're lost and confused and you just want to talk and giggle and do everything else, but that gets you nowhere. So let's explain again.
Yeah, that lost before too. She's explaining what you were doing.
This is what I didn't do. This is the shortcut. I did not apply the shortcut here.
Oh, okay. Okay, then do what you did there. Yeah. Just say what you did
The
there.
negatives, and then you like turn it into a positive.
Yes, and I'm gonna do it again. So here we go. Because this negative doesn't only apply to the 2x, it also applies to the negative 6. And a lot of times you guys forget to apply it to that.
So the negative in the middle applies to the negative.
This right here, I can't just subtract 2x. I also have to subtract negative 6 before I combine. Okay? So the negative applies to the 2x and the 6, which is why it made this a positive. So when I'm combining, it's x plus negative 2x, which makes what? Negative 1x. And it's 1 plus 6, which makes 7 all over x minus 3.
Wait, so you don't do it to the bottom?
If you have the fraction 1/2 plus 2/2, what is the answer? 3/2. Did I do anything to the bottom when the denominator is the same? No. You do not do anything to the bottom of fractions with a common denominator when adding and subtracting. Okay? Yes,
Why is it negative 1x and not negative x?
Well,
it's the same thing.
Oh, I thought it was like some.
I just did it so that we would see the math. I didn't want to make it disappear and everyone's like, we're done. So that was gonna be the hard part here. Now we follow our 3 steps. Step 1 is identify your x-intercept. Where is my x-intercept? X equals 7.
Oh.
X-intercepts come from your numerator. If I set my numerator equal to 0, what is it going to be? 7. Okay? Next, we find our vertical asymptotes or our holes at x equals 3. There isn't one.
Wait, how do we know if there's a hole again?
It eliminates from the numerator and the denominator. Okay, yes?
Yep.
So on our line, we have only 3 and 7, correct? And you're gonna just choose test points to the left, middle, and right. So to the left, if I plug in 0 into my equation, either it's a negative, right?
Okay, you lost me. Wait, when you put in 0,
Sometimes, most times.
which function you put it into?
Doesn't matter.
Oh, okay.
I mean, it matters this one. I'm sorry. It does matter.
Oh.
This one.
So we're putting it in that one.
Because we're comparing the zeros here. Thank you. Sorry. I didn't mean to say it doesn't matter. It does matter. Good question. All right. Now we choose a number between here. 5. So we have negative 5 plus 7 is what? 2. Negative 5 minus 3 is? 5 minus 3 is 2. My bad. 2. And that's what? Positive. And then any number to the left? It's going to do 8. Is that cool?
Yeah.
What is negative 8 plus 7? Negative 1. What is 8 minus 3? 5. So I have a negative divided by a positive, which makes it a negative. So it says, when is it less than or equal to 0? There we go. negative infinity to 3, and then and 7 to positive infinity. And why is there a bracket at 7? It's defined. Okay, well, C is meant for you to do. Okay, your hint for C is everything is parentheses because notice is not equal to anymore, right? So even if I have an intercept, it's not saying when are you equal to 0, right? So everything is just parentheses. When I only have strictly less than or greater than, everything is. All right, follow the 3 steps. Go. All right, so first again, always find your x-intercept. What is my x-intercept? 3. Next, you're gonna find your vertical asymptote or holes. Do I have VA or holes? No holes. Third, we create our number line. So we're at -1 and 3. So I test the point. If I plug in -2, that's -5 over -1, which is a positive. If I plug in 0, that's -3 over 1, which is a negative. If I plug in 4 minus 3 is 1, 4 plus 1 is 5, so that is a positive. I want to know when I'm greater than, so I'm looking for my positive. So we should have got negative infinity to -1 union 3 to infinity. And everything is a parenthesis because it's strictly greater than. Are we good with inequalities of rational functions?